Okay, so let's go ahead and do the other review. So this is the one that's dated April 3rd, 2009. So I don't know if to call this the first or the second one, but it's the one from 2009. And this one is actually very similar to the other review that I did. There's only there's really only about 2 questions that are different. So if you followed the other one, you should be good on most of these, and you should be able to do them. But I'm going to go ahead and do the full review, anyways. Okay, so the first question says determine which of the following vector fields is the gradient of a function. If it is, find all such functions. Okay, so the first one, A, is it gives us v of xy is 3x squared plus e to the y I plus x e to the y minus 7y cubed j. Okay, so we assume for a second, assume that v is equal to the gradient of some potential function. So we say that v is a potential if it's the gradient of some function. Okay, so what does this mean? This means that df dx is equal to 3x squared plus e to the y. And it also tells us that df dy is equal to x e to the y minus 7y cubed. Okay, so to check if this is a potential function, to check if this f exists, then we check the mixed derivatives. So d squared f dy dx. So I do the y derivative of this partial with respect to x. So this is just going to be e to the y. And I do the same thing over here because we know that these two, if I do it the other way around, the x derivative of the partial with respect to y, these should be the same. And here what I get, so if I do the derivative with respect to x, I just get, again, e to the y. Which is true. Since d squared f dy dx equals d squared f dx dy, since I can switch the order, I know f exists. Okay, so now let's try to find it. So if I integrate df dx with respect to x, I'm going to get, that's going to be x cubed plus x e to the y, right, because this is a constant with respect to x, plus some constant. But remember, y is a constant with when we integrate with respect to x, or sorry, when we do all this, right, x is our variable. So really, this is going to be some function of y plus, some actual constant. And if I integrate this with respect to y, the y component with respect to y, this is going to be x e to the y minus 7 over 4 y to the 4 plus some function of x, right, some terms involving x only, no y's, plus, an actual constant. So here, right, this is a function involving only x. That's going to correspond to this one right here. And this is a function involving only y. That corresponds to this right here. And here we see that this term is the same in both of them. So I only need to put it once. So I have f of xy is equal to x e to the y plus the terms involving only only x. That's going to be x cubed plus the terms involving only y. That's minus 7 over 4 y to the 4th plus a constant. And that's my f. Okay, so now for part B, we know that we're given that w is sine of x plus e to the y I plus x e to the y minus 7y cubed j. So we do it like before, except this time I'm going to use g instead of f, just so I don't get the letters confused. W is the gradient of some function. This is an assumption. So this means that dg dx is equal to sine of x plus e to the y. And I'm going to be doing the same thing as above. So here, d squared g dy dx, derivative with respect to y. Let's see, that's going to go away. So this is just going to be e to the y. Okay, now over here, I know that the derivative with respect to y, that's going to be this thing. So that's going to be x e to the y minus 7y cubed. And now I do the derivative with respect to x of that. So that's going to be e to the y. Did I copy that down right? Yeah, that looks right. Oh, no, I'm sorry. I didn't copy it down right. That's the function from before. This is supposed to be cosine of x, y, plus e to the y. No, e to the x. There we go. That looks better. Okay, so this is going to be my y derivative of the gradient, or y component of the gradient. So this is going to be cosine of x, y, plus e to the x. And then I do the derivative with respect to x of that. So derivative of cosine is negative sine x, y, right? Y is just a constant, and plus e to the x. So in particular, they're not the same. So I can say since d squared g dy dx is not equal to d squared g dx dy, right? This can't be possible. If g has two derivatives, then these two derivatives are supposed to be the same. But since we see that this is not the same, we can say that no such g exists. Okay. So next question, number 2. We're given f of xy equals 3x squared minus y squared. R of 0 is 2, 3. Oh, that's nice. It gives us r prime of 0, which is 3, 5. And it tells us that h of t is the composition of f with r. Okay, and it says find h prime of 0. Well, so h is the composition of these two, so I have to use the chain rule. So h prime of t, That's going to be gradient of f at r of t dot r prime of t. Okay, so we want h prime of 0. That's going to be gradient of f at r of 0, r prime of 0. And so r of 0 we know is 2, 3. So, okay, I need to find the gradient. What is the gradient? Gradient of f is going to be the vector, what is that, 6x, and then minus 2y. So the gradient of f at the point 2, 3, right, because that's r0, that's going to be, I'm going to switch this to a row vector. It's going to be 12 minus 6. Okay, so this is gradient f at 2, 3 dot r prime at t equals 0, which is 12 minus 6 dot 3, 5. So that's 36 minus 30, which is 6. And that's all for that one. Okay, so this next point, this was the one that I blanked on this morning. It's actually simple. This is it says find the point on the curve y squared minus x squared equals 1. Closest, let's see, find xy on such that y squared minus x squared equals 1. That is closest to the point 0, 4. Okay, so I was close, but the part I was missing was that this is a problem for, it's a minimization problem. It's a constrained minimization problem. We have a minimization problem. We want to find the point closest to 0, 4. We want to minimize the distance to this point, but we have the constraint that x and y have to satisfy this. Okay, so what is it that I'm minimizing? Okay, so the thing that I'm minimizing is usually called the objective function. But what am I minimizing? I'm minimizing the distance from I'm minimizing the distance of this from this point. So the distance from x to 0 plus y minus 4 squared. Right, this is the distance to this point, and that's what I want to minimize. Okay, but I'm given the constraint. What is the constraint? So if I say g of xy is y squared minus x squared, right? I have the constraint that g of xy is 1. Okay, so why did I make this g? When I have a constraint, right, a condition that has to be satisfied in addition to the minimization problem.
Mic off. Mic on.
When I have a constraint that has to be satisfied, right, some condition that has to be satisfied in addition to the minimization problem, I'm going to use a Lagrange. I want to write this constraint as a level set, right? So this is the level set of G equals 1, right? So the set of all the points that satisfy this such that this is 1. Okay, so now I'm going to use a Lagrange multiplier, introduce a Lagrange multiplier. You know what, let me call this F. Okay. So we have this Lagrange multiplier, and we want to satisfy this. I'm not going to go into where this comes from, but just know this. So let's figure out the gradient of these two functions. So gradient of f is partial of this with respect to x. So this is going to be, let's see, what is this? This is x squared plus y minus 4 squared. So that's the x derivative, that's going to be 1 over 2 root x squared plus y minus 4 squared. And then I have to use the chain rule, so times 2x. The 2's cancel. Okay, and I do the same thing um, with respect to y. So I do the derivative with respect to y, so I get 1 over 2 root x squared plus y minus 4 squared multiplied by the derivative of what's on the inside of the square root. That's going to be 2y. It's going to be 2y minus 4. There you go. 2 times y minus 4. And again, the 2's cancel. Okay, so over here, I have the gradient of g is going to be, that's going to be minus 2x, and this is 2y. So if I write this constraint, if I write this out, I have 3 equations that I know. So the first one is, right, that the x over square root x squared plus y minus 4 squared is equal to lambda times minus 2 lambda x. The second one is that y minus 4 over, same thing, is equal to 2y. And finally, what's the third equation that I have? So I know that y squared minus x squared has to be equal to 1. So this is the system that I want to solve, right? This is the system that I want to solve. I want to find x and y where this is satisfied. Okay, so let's go ahead and start solving. Oops, I forgot a lambda. So usually what you're going to do is first you're going to solve for lambda, okay? And in this case, that's not terribly difficult. So from the first equation, I'm going to call this 1, 2, 3. So from 1, what do we have? If I cancel x on both sides and divide by 2, I have that lambda equals negative 1 over 2 root x squared plus y minus 4 squared. Okay, and then I plug that into 2. So that gives me that y minus 4 over this square root thing equals 2 times y over, um, hold up, that shouldn't, oh, yeah, over minus 2, oh, there we go, that's what it is. X squared plus y minus 4 squared, right? So this came from the lambda, I just substituted it in, right, this. So this cancels on both sides, and I end up with y minus 4 equals minus 2y. Move stuff over, and I have y equals 4 over 3. Cool. Now I use this and I plug it into the final equation. So I have, so this is using 2. Now I use 3, which gives me 16 over 9 minus x squared equals 1. Move stuff around, and I have 16 over 9 minus 9 over 9 equals x squared. And this tells me that, what is that, 7 over 9 equals x squared. So x equals plus or minus root 7 over 9. Okay, so this tells me that I have critical points at um, root 7 over 9, 4/3. Nope, that's not over 9, that's over 3. And at minus root 7 over 3, 4/3. Okay, I'll come back to those because now I'm going to solve for lambda using number 2. Does that help us? So if I divide both sides by y, yeah, okay. So here I'm going to, if I solve using 2, I'm going to have lambda equals y minus 4 over 2y root x squared plus y minus 4 squared. Okay, so now I plug that into 1. So now I plug that into 1. I still need 1. I have x over root x squared plus y minus 4 squared. Right, that same thing equals minus 2x times y minus 4 over 2y root x squared plus y minus 4 squared. So just like last time, I cancel this on both sides, and I end up with, so now I can scroll down. I end up with 2xy, right, I multiply both sides by 2y, equals minus 2. I'm going to distribute the minus 2x, so minus 2xy minus plus 8x. Okay, so I add this to both sides. I have 4xy equals 8x. And actually, let me move this to the other side. So I have, and factor out the x, or the 4x, y minus 2. Yeah. So this tells us either x equals 0 or y equals 2. So I need to check both of these. So I'm going to plug these in to number 3. So if I take x and plug it in there, I have y squared minus 0 squared equals 1. It implies that y equals plus or minus 1. So that gives me the points 0, 1, 0, minus 1. Okay, and I also have the case where y is equal to 2. So if I take that and I plug it in, I have 2 squared minus x squared equals 1, which is 4 minus 1 equals x squared. Tell me that x equals plus or minus root 5. So that gives me the points root 5, 2 minus root 5, 2. Okay, so I have all of my critical points. So these are all of the points where this could be possible. Now I want the one that actually gives me the minimum. So the only way to check that is to actually plug them in to figure out what is the distance from that point to the point 0, 4, see for myself. Okay, so the distance from 0, 1 to the point 0, 4, right? That's going to be square root of 0 plus 1 minus 4 squared, which is, that's minus 3. That's just going to be 3. Okay, distance from 0, 1 to the point, from 0 minus 1 to the point 0, 4. That's going to be square root, this again is 0 plus minus 1 minus 4 squared. That's going to be 5. So 3 is the winner so far. Let's keep going. Um, distance from, oh boy, no, that's not that bad. Okay, so I have root 5, 2 to 0, 4. That's going to be 5 plus 2 minus 4 squared. That's 2 minus 4, that's minus 2. Squared is 4. So that's going to be square root of 9, which is 3. So that's tied for the minimum so far. I do the same thing with negative, and that's going to give me this exact same thing. Minus root 5, 2. That's the same thing. Okay. So let's try these ones. Plus and minus root 7 over 3 and 4 over 3. So the distance of root 7 over 3, 4 over 3 to 0, 4. That's going to be 7 over 9 plus 4 over 3 minus 4 squared. Equals, okay, so I'm going to factor out the 1 over 9. I get 1 over 3 root 7 plus 4 minus 12 squared. 4 minus 12, that's negative 8. So it's 1 over 3. That's negative 8 squared is 64. And it's going to be 7 plus 64, which is 71. Which is definitely bigger than 3. Oh, actually, hold on. No, it's less than 3, right? Square root of 81 would be 9, and 9 over 3 is 3. So this is less than 3. And if I do the same thing for negative 7/3, I will get exactly the same thing. right? Because when I square this term, it comes out to be 7 again, or 7 square, 7, positive 7 again. So this works out to be exactly the same. Okay, so I'm going to say that the answer is going to be either the point minus root 7 over 3, 4 over 3, or root 7 over 3, 4 over 3. Now, if you see a mistake, it's possible because I thought I was supposed to get only one answer, but I will take this. So here I'm just, how did I pick these two? I'm just, oops, that's supposed to be root 71. I'm just picking the points here with the smallest value of our objective function, the smallest distance um, to the point 0, 0.04. So root 71 over 3, I don't know what that is. I know it's less than 3 though. So that's why, and they have the same value. Both of these have the same distance to the point. So those are my answers. Okay, number 4. Find an equation for the tangent plane to the surface x y squared plus 2yz squared equals 40 at the point 1, 2, 3. Okay, so first we want to find the tangent plane. So the way I do that, I start off by moving any variables I have over to the left-hand side and any constants over to the right-hand side. So looks like it's already done. So this right-hand side I'm going to call g of x, y, z. The normal vector for the tangent plane is going to be the gradient of g. Why is that? Well, g here, right, well, this curve, this surface, whatever this is, describes a level set of g equals 40, right? It's the level set g equals 40. And we know that gradients are orthogonal to level sets. So the gradient of g is orthogonal to the surface described by this set. So that's really the vector that we want. So the gradient of g, right, and g was the thing that I get when I move all my variables to the left-hand side. Okay, so this is going to be y squared, let's see, 2y, so the derivative with respect to y, so that's going to be 2xy plus 2z squared, and this is going to be 4zy. But we're interested at the point 1, 2, 3. So gradient of g at the point 1, 2, 3. So I'm just going to plug these numbers in. I get, so 2 squared is 4. Here I'm going to have 1, or 2 times 1 times 2, that's 4. Oops, 4 plus 2 plus 3 squared. Okay, and then I have 4 times 2 times 3. It's 24. So that's going to be 22 there in the middle. Okay, I'm looking for the tangent plane. Okay, so actually, once I have this, I can write this down right away at this point. I can write down 4 times x minus 1 plus 22 times y minus 2 plus 24 times uh, z minus 3 equals 0. Or if I wanted, if you're more familiar with the way we did at the beginning of the semester, I can do x, y, z dot with my direction vector, which is 4, 22, 20, 24, equals 1, 2, 3 dot 4, 22, 24. Either one of these works, right? They both describe a line. This one's a little bit faster. So this gives me 4x plus 22y plus 24z equals, that's going to be 4 plus 44 plus 72, which is, how do I want to do that? So that's 116, 120. So I have 4x plus 22y plus 24z equals 120. I can simplify that by dividing through by 2. I have 2x equals 20 plus 21, that doesn't look like a 2 anywhere, plus 11y plus 12z equals 60. Either one of these is fine, and they're both equivalent. Okay, so part B, I still need the same values from up here. It says find equations for the normal line to this surface at this point. Okay, so I want to find the line normal to the surface at that point, right? So if I have some surface, right, I want to find the equation of this line. Well, so here we know that this direction, it's going to be the same as the gradient, right? Because we know that it's orthogonal to the surface. So the direction vector for our line is going to be the gradient of g. And we already know what that is. All right, so we know gradient, let's see, so this is b. The direction vector, so this was our normal vector. Our direction vector is going to be the gradient of g, which we know is 4, 22, 24. And we know that a point on the line is the point 1, 2, 3. So we can write the equation for the line x, y, z of t is going to be 4, 22, 24, t plus 1, 2, 3. So this tells us that x of t is 4t plus 1, y of t is 22t plus 2, z of t is 24t plus 3. And that's my answer. Okay. Moving on to 5. It says find a unit vector in the direction in which the function f of x, y, which is ln of 1, 1, 2x, sorry, plus 12x plus 6y minus y. So it gives us this function and says find a unit vector in the direction in which this function increases most rapidly at the point x, y is 0, 0. Okay, so at a given point, right, we can look around and look in what direction does the function increase most rapidly. So if I change positions, the direction that it increases is probably going to change as well. So that's why it's important that I care about which position I'm at. But the direction of steepest increase is going to be the direction of the gradient of f. Right, so this direction is going to be this at this point. So let's evaluate the gradient. So the derivative of this with respect to x, that's going to be, it's going to be 12 over 1 plus 2x plus 6x. 12x. And 6 over 1 plus 12x plus 6, sorry, this should have been y, 6y, minus 1. And we want to evaluate this at 0, 0. So that's going to be 12, and then we have 6 minus 1, that's 5. Okay, so this is the direction in which this function is increasing most rapidly at this point. Okay, or so let me say it the other way around. At this point, this is the direction which the function is increasing most rapidly. So we're almost done. We want to find a unit vector. We want to normalize this, right? So write it this way. This is going to be square root 144 plus 25 square root of 169, which is 13 squared. Yeah, 13 squared. Okay, so my unit vector is going to be 12 over 13, or 5 over 13. And that's my answer for part A. For part B, it says, what is the directional derivative of f in this direction? Well, how do we compute the directional derivative? It's just going to be gradient of f at this point dot d hat. So remember, we dot it with a vector in that direction, but we have to use a unit vector. Okay, so that's the unit vector. So I could just do this. This is going to be 12, 5 dot 12 over 13, 5 over 13. And I could keep doing that, and that's fine. But one thing to notice is, how did I get this d hat? Right, this was gradient of f at 0, 0 dot, well, what was d? D was the gradient of f at 0, 0, and then I normalized it. So that's this. Right, this is what d was. And I'm just going to put gradient of f, but that's at the point 0, 0. So this is the same as the norm of gradient of f squared, right? A vector dot vector, that's the same as the norm squared over those cancel. And this is the norm of the gradient of f at the point 0, 0, which incidentally I already computed, right? It's right there. This is 13. Okay, so that's only because I was only able to make this shortcut, and it's not really even that much of a shortcut, right? This would have been, I would have done 12 squared plus 5 squared over 13, and I know that's 169 over 13, which is just 13. Same thing. But I was able to make this little simplification because I know that it's the direction of steepest increase, which is the gradient already, right? So in general, that's not the answer for a directional derivative. If we want a directional derivative, like we're about to do in the next problem, we start with this. Okay, so it says find the directional derivative of f in the direction of d, which is 3 minus 4. Okay, so like I said, this needs to be a unit vector, so let's normalize it. It's a 3, 4, 5 triangle, so that's going to be 3 over 5 and a minus 4 over 5. Okay, so gradient of f at that point dot in this direction 3 over 5 minus 4 over 5. That's what it was 12, 5. 3 over 5 minus 4 over 5. That's 36 over 5 minus 20 over 5, which is going to be 16 over 5. So at the point 0, 0, the slope in the direction of the vector 3 minus 4 is 16 over 5. Okay, question 6. We're given f of xy is fxx plus, nope, sorry. We're given that this is equal to x e to the y plus y e to the z plus z e to the x. And it says compute fxx plus fyy plus fzz. So again, like I said in the last video, this is the same as d squared f dx squared. This is d squared f dy squared. Okay, so it's just the second derivatives with respect to each of the variables. So let's get computing. And I have df dx. Let me just write it as fx. So that's going to be e to the y plus z e to the x. fxx, that cancels, or the e to the y goes away, so we're just left with z e to the x. Okay, fy, that's going to be e to the z plus x e to the y. fyy, e to the z goes away, so this is going to be x e to the y. And finally, fz, so we have y e to the z plus e to the x. So fzz equals what? So this is y e to the z, and that goes away. So our final answer, fxx plus fyy plus fzz, z e to the x plus x e to the y plus y e to the z. And that's my answer. Okay, last question. So we're given a function, f of xy, which is x cubed minus 27x plus y squared minus 6y. It says find all of the critical points and determine for each one whether it's a maximum or minimum or saddle point. So the first thing I do to find the critical points is I take the gradient, right? We take the derivative, set it equal to 0. So I find the gradient. This is going to be 3x squared minus 27. And then this is going to be 2y minus 6. So that's my gradient, and I set that equal to the 0 vector. So that tells me that 3x squared minus 27, so solve for x squared. This gives me 9. X is plus or minus 3. And then here I have 2y minus 6 equals 0, so y equals 3. So that means I have two critical points. I have the points 3, 3, and the point 3 minus 3. So these are my critical points. Now I need to determine if they are maximum or minimum or saddle point. Local max, local min, or saddle points. So to do that, I'm going to create the Hessian matrix. Okay, so this is the matrix of all of the second derivatives. So this is d squared f dx squared, d squared f dx dy, d squared f dy dx, and d squared f dy squared. Okay, so I already have the gradient, so let's start taking the derivatives. Um, so this is going to be, so I do the x derivative of the x partial with respect to x, and that's going to be 6x, okay? And then I do the derivative of that with respect to derivative of the partial with respect to x, derivative of that with respect to y, that's just going to be 0. And then that's going to have to be the same, right? Because I can interchange or swap the order. And then the derivative of this with respect to y, that's going to be 2. Okay, so notice this depends on x and y, right? Um, so let me write this as x, y, right? It's a function of x and y. So h at 3, 3, that's going to be 18,002. So the determinant of this is going to be uh, positive 36. Okay, so specifically that's bigger than 0. If it's bigger than 0, I need to check the sum of these two, or they're going to have the same sign. Okay, so, but I need to check if one of them is positive, or if they're both positive. So I have 18 plus 2 bigger than 0. This tells me, oh sorry, so this one right here, this tells me it's a max or a minimum. This one right here, if it's bigger than 0, this tells me it's a minimum. Right, so it's like when I have a second derivative, if I have that df dx squared, if this is bigger than 0, right, so that means it's convex or concave up, right? So if I have a point where that's true, then it has to be a minimum, okay? If it would have been the other way around, this is less than 0, that's like this. Okay, so don't get that confused with this determinant though. If the determinant is negative, we have a saddle point, which I believe is what happens next. H of 3 minus 3. No, actually, okay, so, oh, yes, yes, it does change. Sorry. This is not minus 3. This one should be minus 3. Right, okay. So here we have minus 18,200. So this tells me the determinant at this point, it's going to be minus 36. Specifically, it's less than 0, so it's a saddle point. Okay, so we have this one is a saddle point, and this one is a local minimum. All right, and that's review number 2.